important, and I'm going to give this lecture in two parts. The first part I want to talk about water cycling, so because there'll be a lot of talk about biogeochemical cycling, so this is basically the first cycle, it's water. And then I'm done with that, I'm going to talk about some of the properties of water. I'm hopeful that, given your backgrounds, a lot of this, you took wetlands from me? Mm-hmm. Yeah, okay, so a lot of this would be, you've probably had some of this in some of your other classes as well. So hopefully it'll be stuff, I knew all that, but I just you gotta make sure you do know it, because when we start getting into redox and soils, things like that, you need to know that. So, okay, so I'm going to deal first. So there is the global cycle of water, just to sort of outline that before I go on any farther here. So basically what you have water in the atmosphere. Where else do we have water?
The ocean.
Ocean, that's easy. Okay. Ice caps. And terrestrial. Okay. In this class, when we talk about movement of water, I'll often use the word flux. Flux just means movement. Okay. So atmosphere to the ocean is probably one of the major fluxes. That's precipitation. And atmosphere to the terrestrial is also precipitation. It's not even we're talking about that one. You got an exchange from the ocean to the ice caps back and forth. And of course, the flows back are evaporation. And then terrestrial to the ocean. I'm going to be using the term stream flow. So all of limnology pretty much just deals right here. It's terrestrial water, and so basically this is what we call the global cycle. Very simple. It has four major components, several fluxes back and forth. That's not good. But that's one way of looking at it. Another way of looking at flow or basically cycling is more of a regional component. And by this, every different area of the world, every different biome, every different habitat probably has slightly different water budgets. So, for example, we'll be talking about wetlands. I'll be talking about tidal wetlands, and tide flow is a big one. But around here, it's not. Okay, tide flow is not important. So I'm going to be using what the local regional water cycle I'm going to be talking about was what is classically in this part of the world as we were basically temperate deciduous forest. So I'm going to be talking about water cycling in temperate deciduous forest. Where I'm going with that. Okay. So there are 10 components. First component. Let's go ahead and reset now. Everybody, it's not that exciting. And plus that I'll forget later and walk out, and somebody wonder why I'm a bad Department of Citizen. Okay. So the easiest cycle to ever understand is basically, of course, it's precipitation, the movement of atmospheric water down. Okay. So all I'm talking about is it's coming down. I haven't said where it hit yet. Okay. Where does it hit? Where does water hit?
Everywhere.
In a temperate deciduous forest.
The canopy?
Right, it's not, yeah, so the idea is it doesn't hit the ground. And that's it's an important step in the water cycling here. And so it's as if I was standing over here with a football and I threw it to Caitlin and Haley grabbed it. What do we call that? Interception. Okay. So basically that's what happens in a lot of the total amount of rain that hits down doesn't necessarily go to the ground. It gets hit on the leaves, and the leaves hold it. Okay. And now, water that's been intercepted, two different things can happen. It can either fall off the leaf and head to the ground, or it can be evaporated back into the atmosphere. Okay. So that's probably, much of the water is going to be evaporated straight back in the atmosphere. So, precipitation, has somewhat of a seasonal cycle. Interception has a huge seasonal cycle. Interception is extremely high during the growing season, but very, very low during the dormant season, because there's no leaves there to catch down here. Okay. So as a result, evaporation has the same sort of effect. Evaporation during the growing season is not only is it the fact that it's warmer, but because you've got interception going on, you're going to get more water coming back. So, what this is all going to lead to is, as we start to talk about the different places where water can be, is these sort of things have an effect. So nothing is stable. Everything is going to move, but it often has seasonal cycles. And so, if the precipitation is strong enough that basically the water reaches the holding capacity of the leaves start to droop, the water starts to fall off. We call that through fall, and that's what you're seeing right here. There's a similar event, so we always consider these two things the same because it's really what's happening. It's intercepted water now moving down to the ground. The other one is called stem flow. And what that is, that's just water running down the tree. Okay, so if you've ever worked on anything and like a pipe or something up high or a shower head, next thing you know your armpits are wet, that's stem flow. You're the stem. Okay, things are coming down. So I'm sure you know people do home repairs that might have faced with that several times. So some people. So anyway, so these through flow and stem flow, as far as you're concerned, they're one flow. They're just one flux together. Okay. So here's the picture of basically all that's happened. Here's the tree, and you can see precipitation coming down on the tree itself. This is stem flow coming down. Here's through fall over here, and evaporation going back up, and then showing in this picture that there's places where there is no interception. The rain hits straight to the ground. So it's sort of a nice summary picture of all that. I found that. Okay, next up. Okay, when the water hits the ground, basically it's absorbed by the ground. That's called infiltration. And lots of things determine the rate of infiltration. The particle size of the soils. The larger the particles, the faster the infiltration rate. The smaller the soils, the less it is. You get really small soils, clay soils, infiltration is very, very low. Also, the size of the storm event is going to decide that as well, too. So, and the last thing that decides infiltration rate is known as, and here's another new word for you, antecedent moisture condition. Okay. So if it started raining right now, what do you, outside, given what our conditions, what would the infiltration rate be? Low, medium, high? High. Why? It hasn't rained anyway. The antecedent moisture conditions are low. Okay, that's why. But earlier this year we had rain after rain, and all of a sudden it was flooding very easily. The antecedent moisture conditions were such that infiltration was very low. So again, so this was basically, you're looking at ponded water here that's basically infiltrating down through the soil.
So infiltration is when the soil has reaches like capacity for water and it's flowing back.
No, we haven't got to that. So basically, and it doesn't run back.
Yeah.
We'll talk about that in a minute. What infiltration is the movement of water on the surface into the ground, into the soils. Okay. Now, once water is in the soil, okay, another event will happen, if, and this has, which is with major seasonal development, and that's called transpiration. Okay. So what happens if trees, plants, and all that, of course, the water enters into the roots and is carried through the tree by cohesive tension. And make sure you understand the problem. Remember, it's not pumped up the tree. Okay. It's the water is never pumped up. Well, I'll talk about that. It's pulled up the tree. It's pulled from the leaves down. You can pull, and when we talk about the properties of water, I'll talk about how that happens. And so this water then goes to the leaf where it's used in photosynthesis, and a lot of it evaporates out through the stomata. Okay. So this is a loss of subsurface water. Okay, I should probably hear some terms of so basically we had the surface to subsurface. It just means just below the surface. And I define that as infiltration. So some of this water to the subsurface travels through the trees back to the atmosphere. And that's called transpiration. Does transpiration look like any of the other flows I've talked about so far? Who does it seem to be most similar to? Movement of water back to the atmosphere.
Evaporation.
Very similar, yeah. In fact, in some models, when they talk about it, they make one word. They refer to evapotranspiration. But I'm a stickler. They're not the same things. Evaporation is water on surfaces, either infiltrated water, or either intercepted water or surface water back to the air. This is subsurface water back to the air. And this has a major biotic component. So as a result, what you see, if I ask you what time of the year are rivers the highest, what would your answer be? Spring, okay? That's basically what's happening in the spring, is you have no infiltration because the leaves aren't on yet. Or no interception, the leaves aren't on yet. You get a lot of infiltration, but you're getting no loss through transpiration back up. So eventually all that, and I haven't got to the end of that story yet, all that water, instead of being returned to the atmosphere, is now heading towards stream flow, getting that way. Basically what's happening. So all these things are working together to give us these seasonal cycles. It's not that we get more rain in the spring, it's just the more rain, the rain is more effective. Okay. So here's that term. Evaporation and transpiration are often considered together. So in some people it doesn't matter. For us it matters because we're biologists. But if you're working in wetland systems, you talk about basically water leaving the wetland. You don't care how it gets out of the wetland. And so they use the term evapotranspiration. Okay, here's my summary slide of all that. Okay, just added to my picture here. Okay, I haven't got to this yet. So here's I got my interception going on. So and here's precipitation, and they refer to this as, I see this term in case of gross precipitation. This is everything that fell, but it's not going to be everything that reaches the ground. Okay. So a lot of it's going to be intercepted. Here it goes back by evaporation. Here they're not showing transpiration as well here, because they're mostly showing that. And some of it's going down into infiltration into the soil. Okay. Now there's other fluxes here we haven't discussed yet. Okay. The first one I want to talk about here, and again, I'm really kind of a stickler on all of this because it's not all the same. The first thing is when water is infiltrated and it gets into the soil, and as Ada was mentioning, the soils become saturated. Once soils are saturated, so as long as soil is not saturated, it can be added water to it, and the soil will cling onto it and hold that water. But once it becomes saturated, you can't hold any more water, the water starts to move. Okay. and it's gonna move in response to topography. It's gonna move downhill. So if I've had water, if I have a hillside, and water's, something like, if I draw a hillside here, I've had all sorts of precipitation coming down here and hitting this. If my soils are dry, I've got a lot of, basically I can store water in these soils if they're dry. Okay. But once those soils are now saturated, this water will start to move. It starts to move downhill. Okay. That's called subsurface flow. And subsurface flow, again, is got a kind of a seasonal component to it, depending on how much rain is getting through, all that. And it's water movement right below the surface. Do not confuse it with groundwater flow. Groundwater flow, it's the same sort of, I have water moving through saturated soils, but it's much deeper. And groundwater flow doesn't have much of it, it's relatively constant. Subsurface flow can move to groundwater flow. As that stuff's going down, it can help recharge groundwater flow. But there isn't, groundwater flow really doesn't change as quickly as subsurface flow. It changes very slowly. Okay. Now, I've got my situation here. This hill is a good, that I drew here is a good example. I've got a situation where I have rain taking place. Okay. And I've got through falls coming down through here, hitting this soil. Antecedent moisture conditions were such that this soil becomes saturated and it's moving down here, but the rain keeps coming. Okay. So it can no longer be infiltrated, and so it starts to move on the surface. Water across the surface. This is called overland flow. So you've all seen overland flow. Ever been in a parking lot when it rains? You see these, overland flow tends to move in sheets. It's not in a constrained channel, okay? It's basically just moving water. It can be kind of destructive, depending on where it's at, okay? Overland flow. Eventually though, remember, everything seems to be following topography. So eventually, water is going to be moving into a stream channel. Okay, so you get down to the base where all this water comes together. So in many cases, what you see is that if there's overland flow, it's going to flow into a stream channel. Subsurface flow comes down, it's been moving through the surface, and finally it hits that channel. The channel is incised the subsurface area, and so it moves out that way. Precipitation could be falling directly into the channel. Everything goes to stream flow eventually. So it's kind of the major point here. So here's basically showing you this sort of thing here. So again, what they're showing here, this is groundwater flow. Groundwater flow is and basically the top of groundwater flow we refer to as the water table, because this is pretty much permanent water. And the water table runs here, and I've got the stream incised here. So as a result, it cuts down into the groundwater. So part of that flow is due to groundwater. So that's why streams, they can be a very, very dry season, not much rain at all, but the stream is still running. That stream has access to groundwater flow. Infiltration is taking place. Here's my subsurface flow that I talked about before, coming in below the surface here. They're also probably be moving from subsurface flow into groundwater flow over time. And then here's the overland flow coming in here. So everything eventually gets to the stream. Again, here's another position here, another picture that says the same thing. So when you look at water in a stream, it's flowing a stream, it has various different components feeding the water to that stream. Groundwater, subsurface flow, surface flow, precipitation, all add to that stream. And they hit the stream at different times. Okay, so groundwater flow is always there. The first thing if I have a storm event, the first water, when the stream starts to rise, what's causing the first part of the rise is precipitation coming directly in. The second part of the rise will be then anything that comes from subsurface flow, from overland flow. It's gonna be the next thing that comes in. Subsurface flow then be last, and then of course the groundwater's always been gone there. So as a result, I think I have a picture of some hydrographs. Multiple stream influences. So this is basically, if you look at streams, okay? See, so discharge is never constant. Okay, so that's what I wanted to talk about. So let's see. Discharge. Okay. The international symbol for discharge, we're talking about discharge. It's how much water is moved in a stream per unit time. And so it's a volume of water. So common ways of measuring water are cubic meters per second. If I'm talking about a large river, Mississippi River, I'm talking in millions of cubic meters per second. Okay. Sometimes it's cubic feet per second. Okay. It's always very interesting. So as scientists, we would talk about cubic meters per second. But if I'm dealing with USDA or Army Corps of Engineers or something, we're talking about cubic feet per second. Okay. On small streams, it's often measured as liters per second. So it's how much water moves past the point per unit time. Okay. The symbol for discharge is Q. I don't know why. It's Q. When we talk about Q, we're talking about that. And so this is a picture of what a standard hydrograph looks like. So on a normal stream, so basically this is discharge here, how many cubic feet per second. And so basically what's happening here is the stream is flowing, and you notice they're showing you this blue block here. This is what we would call a storm event. So the storm hits the stream, okay, and we don't see a whole lot of change, right? It's not an instantaneous change. Because the only feed in there is direct precipitation. And that's not going to be very big, especially if the stream is somewhat canopied. Okay. And then, after a while, throughfall is taking place. Throughfall, if the soil conditions are such that the soil is already saturated, that water is going to move as overland flow, and overland flow is going to come quickly. Okay? And so, and then as all the water starts coming in, you get what is called, this is the rising limb of the flood. So the rain may have already stopped, but the river keeps growing because it takes it a while through subsurface flow to get there. It then gets there, but if you notice also, it's somewhat steep on this side. Once it starts to go, it goes pretty fast. Okay. Then it hit the rising limb, pretty much the inputs aren't changing anymore, and so then you're on the falling limb of the flood. And you notice it is not as steep. It's much more gradual, because this stuff is going to be slowly coming to the stream, the end here. Okay. What they call here base flow is groundwater flow. And so basically, you see a slight rise in the base flow, and then it finally hits, and the rise is due to the fact that subsurface flow has been feeding the groundwater flow in this process. And then it's going to slowly go back down to normal. So this is what a standard hydrograph, this is the way a river should work, but doesn't, unfortunately. This is what, in pristine streams, this was the standard way rivers would work. Okay. Here's another picture of the same sort of thing here. So here's what they're showing here, this histogram is showing you the storm event, the rain starts, and basically you can see it raising, and then here's the highest part of the rain, and then the rain kind of goes down here. So the rain has started over here, there's that lag time, and then finally direct runoff hits the stream, that's overland flow, shoots the stream all the way back up. And then basically you look at subsurface flow feeding most of this, and then the river drops back down to base flow. Again, this is the classic look, sharp rise, slow fall. And in response to an event with lag times. And these lag times can be fairly long in a natural system. Okay. So base flow, precipitation is involved, that's the storm event. Inputs to the stream then are direct precipitation, which is not a big thing. Overland flow, which is a big thing. subsurface flow, which is a long thing. Okay. And then there's lag times are before and after the peaks. Okay. All right, now, let's change this around some. Let's talk about what happens. That, again, I've been talking about a pristine temperate deciduous forest, which we don't have a whole lot of those left anymore. What we have instead is the effect of urbanization. Does anybody know where that picture was taken?
Montgomery?
Yeah, Memphis. That's Memphis, yeah. This is the view I always have of Memphis, because I spent a lot of time on the river when I was working down there. Okay, yeah, it says city of Memphis right across the road. I didn't notice that. Yeah, guess that might be Memphis. That's, yeah, those are the cobblestones areas, okay. So, how, so what sort of stuff has happened in the world when we've gone from forested area to cities? What are some of the big changes?
Change in topography.
Is that, what do you mean? You mean there's some change in topography, some, I guess you make roads and all that. What maybe it was a bigger change?
Less vegetation.
That's a big one. You cut down the trees, okay? So it's kind of the big thing. There's not a whole lot of trees, okay? So some of the characteristics of urbanization, how do they affect those 10 components? Okay. How does, and let's think our way through this. How was precipitation in this area changed when we went from a forested area to a non-forested? Did precipitation increase, decrease, or have no effect?
It's gonna increase.
How? Why?
Because you don't have that canopy layer.
I don't understand why that would have changed.
Oh, the actual precipitation.
Yeah. Yeah. So basically, there may be some changes, but we'll just leave that as, we don't know. Okay. Assume there were no changes in precipitation. The rains came, rains just as always, okay? What about interception? I have all these buildings. Has interception gone up or gone down? Interception went way, way down. Okay. But it's hitting these buildings, yes. Look at the surface area of a roof. Okay. Now, look at the surface area of all the leaves of a tree that basically takes up that same, two-dimensional area. You have layers upon layers of leaves. One tree has a whole hell of a lot more surface area to catch water than a roof. So precipitation or interception went way down when we did this. What about evaporation? Also down, because you've lost all that surface area. Remember, evaporation is dictated by interception. If you don't have interception, sure, the water's sitting right out there in front of the opening, and it is evaporating. I'm not saying that, but the rate of evaporation is going to go way down. Okay. Through fall and stem flow. What happens to water that lands on a roof?
Depending on if you have like a flat or a slant.
Okay, I've got a slanted roof. Where's that water going to go?
To the ground, it's gonna fall.
Does it fall into the ground? It's going to gutters.
But if you have a gutter,
Yeah.
then it goes.
Yeah. Basically, all that water is quickly gathered and is taken in the ground. So through fall, so again, I've gotten rid of all this evaporation because I have no interception. That water's moving as through fall, and it's moving pretty fast. Okay, so I got through fall is going to go way up. Infiltration. Okay. How much of the water is going to be soaked into the ground?
Not as much.
Kind of hard to go through concrete. Yep. Concrete, and lawns, people, oh, they got a lawn. Lawns have horrible infiltration rates. They're almost as bad as concrete. You've all seen, again, you've seen overland flow. So as a result, infiltration is going to go way down. Transpiration, that should be evident. Remember, that's a biotic component based on trees that we've all cut down. Transpiration is way done. Okay. Subsurface flow also is going to go down. Why? Because we didn't put anything into the soils. Okay. So I've got all this water that we've constrained, and where does it eventually end up? What flow is missing?
Stream.
Stream flow. Okay, so overlap flow is going to go way up, going to be huge, because that water is going to be coming over the surface in gutters. Stream flow is going to shoot up. So basically, what I'm telling you here is what we see nowadays. Okay, the upshot is water now arrives faster to rivers than it did before. Okay, there is no lag time. That's gone. Also, more water now comes to the river, because water that would have been lost through evaporation or slowed down through, lost through evaporation or transpiration is not anymore. It remains as part of the input to the river. Okay. Rivers cannot handle that much water. Okay. The river can only handle a certain amount of water. Okay. And as a result, when we see these floods on TV, I always hear people, that's a natural disaster. There is nothing natural about the modern flood. It's as artificial as possible. Flooding, when people talk about the rivers flooding and how the rivers, flooding is an important component of rivers and how they work. But the flooding was a slow rise of the river, held it for a while, and then an even slower decline, like I showed before. Okay, that's not what we're getting now. Now we're getting these massive, they're called flashes, spiking, where the water rises, comes in, floods everything, and drops fast, okay? So that's basically what's happened here. Is just want to get across what we see floods on TV, and they talk about floods, those are human induced. Those are human activity. Okay, that was part one. How am I doing on time? Can we make it? All right, I'm going to talk about the properties of water now. Again, that's going to be a big thing. So what I was just talking about more is the cycling and all that is kind of a big picture. The properties of water, deal with this. This, by the way, is, anybody know what this system is? You might have driven over it.
Where?
What stream it is? Anybody know?
Is it on UTM property?
It's what?
Is it on UTM property?
Part of it is, but not this part. But yeah, that's Cane Creek. Okay. And Cane Creek looks like all the other streams in this part of the world, deeply incised. This is also not natural. Okay, this is human activity caused our streams to look like they do right now. We'll talk about that later. Okay, so let's talk about the properties of water. Hopefully, again, you all know that water is two hydrogens and an oxygen molecule. And they are covalently bonded, which means, of course, they share electrons. Okay. The molecule is not linear. That's important. It's not an oxygen with the two hydrogens sitting off to the side. It's bent. Okay. Now, one of the important rules of nature is oxygen when it comes to electrons, and this is going to come up over and over in the class. Oxygen loves electrons. Just loves electrons. Okay. So if we look at this molecule, the molecule is not linear. It's bent. You don't need to know that it's 104.45 degrees is the bend. But this distance is almost a full angstrom. The distance from the oxygen to the hydrogens is actually relatively far. When it sits across here. So I've got these electrons that basically is covalent bonds. So these electrons are forming a cloud all around these guys. But what happens is oxygen, so the electrons where do they hang out most of the time? Most of the time they hang out near the oxygen. Okay. So if we look at this here, this pink in this picture is negatively charged, green is positively charged. If the electrons are spending most of their time over here, then in general, this is negative. And since they're not over here, it makes the size of the molecule positive. So water is a strongly polar molecule. It has poles. And as a result, it's like a magnet, and that gives water sticky properties. And it has two different sticky properties. First sticky property is what water sticks to itself. So the hydrogen side of the molecule, the hydrogen side, it tends to be attracted to the oxygen side of other molecules. And this sticky property is known as the property of cohesion. It is a cohesive, water is cohesive. Water sticks to itself. Very important for life. Okay. So the idea, if you think about this, if I was to grab this water molecule here and pull it up, this one will follow. Okay. And one below it will follow it. It'd be like a train. If I had a narrow enough tube and I pulled the water at the top of the tube, it'll pull water up that tube. The other thing water does is it sticks to solid objects. Solid objects tend to be somewhat charged, and so water sticks to it. And that is known as the property of adhesion. So water sticks to surfaces, water also pulls on itself. Okay. And so as a result, water, if I look at water in a tube, in a glass tube, what I see is it's not flat. It tries to climb up the side of the tubes. It can only climb so far, and then its own weight keeps it from going down, climbing power and all that. We've all seen this. This is a meniscus. Okay. So the water here is trying to climb up the tube. How much water is in that? If you had to determine how much water is in that graduated cylinder, how much would you say?
2.6.
You would say 2.6. Why did you measure it from the bottom?
Because you measure from the bottom from this.
Why?
Because if you measure from the top, you're missing that.
But if you measure from the bottom, you're missing this. Okay. Why do we measure from the bottom? Because we had to decide. We had to decide how to do it. They decided, I'll make it the bottom. Okay, everybody, okay, it's just standard convention. We always measure from the bottom. Okay? I do that. Okay? These two things together lead to something which is known as capillary transport. I've actually been talking about capillary transport, but you didn't know it. So first of all, what is a capillary? Capillary is very, very thin space. That's what it is. So we have capillaries in our body, which are the site of oxygen exchange, carbon dioxide exchange in our body. The rest of the arteries and veins are just for transport. The business end of capillary. And you've all seen, these are called capillary tubes. It's a very thin layer of drawn glass. Okay. And basically what it is. And so a thin tube is a good way to describe a capillary, but really it's just thin space, very thin space. Okay, you've all seen capillary transport. Everybody's had a blood test one time or another. And what happens when they touch that capillary tube to the blood? Shoots up the tube to a certain and stops. It's because your blood is mostly water, and that's the action of water through cohesion and adhesion, causing that to happen. Okay, blood shoots up the tube because of capillary transport. This is how water moves. Okay. So this is they show you here is a dish with water in it, and the capillary's been stuck in it, and the water climbs up the tube. Okay. It doesn't climb out the top and shoot out, because what happens as the water comes up, I've got more and more water in here, which means I've got more and more weight being affected by gravity pulling down. And so sooner or later, the water will stop when the gravitational pull equals the transport up the tube, so it stops somewhere. Okay. So, what happens is waters move across the surface. I got that right, yeah. So basically, water in the tube is trying to climb the glass, that's adhesion. And as it climbs the glass, go, hey, everybody come with me. Okay, that's cohesion. And so you have this pull up here. Where is it important? Okay, I've been talking about many ways important. So in subsurface flow, remember water's moving underground. This is why it's moving. Okay, in groundwater flow, water is making its way through these. Basically, if you think of it underground, the spaces between soil particles are capillaries. They're causing water to move. Infiltration, capillary transport down. Very important in there too. And in transpiration, it's important. Okay. Is that the right picture I want? No. Okay, how does water get up again? If you think about it, if I have simple transport, if I put water in a capillary tube, it only goes up about yay far. Okay. How the heck does water get to the top of a tree? Because if you think about how much water is in that tree, a tree that's maybe 50 or 100 feet high, that's going to be real heavy. There's no way the capillary transport by itself can take water to the top of the tree. Very short plants, you see it all the time. Sometimes you see that if you raise tomatoes, if you look at tomato plants first thing in the morning and they're still short, you'll see water drops on the leaves. It's not dew. That's actually capillary transport is brought that up there. Well, once you get any taller than that, capillary transport won't do it. Instead, what causes transpiration is what is known as cohesive tension. Water in the leaves is evaporating and going out through the stomata. Okay, so water in leaf spaces is going out. As it goes out, because of adhesion, or cohesion, it pulls another water molecule into its place. And as that one goes out, it's going to pull another water molecule in its place. Well, remember the xylem is very, 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 very thin tube. So, in there, hundreds of thousands of them. And so what's happening is, the water's being pulled up the tree. And that's what's happening. So evaporation of the leaves is very, very important, or else there would be no water flow going on. You've all seen it. What do you do? What are you supposed to do with your Christmas tree when you first get it?
Water it.
Water. If it's just water, you know what it's going to do? It's going to die real fast. Okay. Why? Okay. What do you do with roses when you first get them?
Cut the base of the stem.
Why? Ever wondered why? When they cut those roses, took them to the store, there was water all the way down through that stem. Well, cohesive tension is still going on, even though you cut that off there. Water is evaporating out of those leaves. What's happening is the water at the bit where the cut is now slowly moving up. The base of the water is moving farther and farther up that. If you were to take that tree, stick it in water, nothing's going to happen because you got an airlock. You got a break in the water. It's not all one water. So you got to cut that off, get up to the fresh, where the water is still nice and fresh, and then stick it in. And then that'll cause it to last longer. Ever see the ones that get me the ones that people who buy a Christmas tree and then put it on the roof of their car and take it home? Can you imagine the transpiration that's taking place from that thing as the wind is blowing past it and all that? You have to take off a couple feet before you get to that. Always cover your tree. Okay. Another cohesive application, because water sticks to itself when you water at the surface, basically all the powers pulling side by side on the surface, and it results in what is called surface tension. So in this case here, so cohesive tension is pulling it up the tree, and then it's surface tension here. This is a water strider using that surface tension to its abilities. Okay? Lots of invertebrates do this. That they can walk on water. Anything small, a lot of insects is not a problem at all to walk across the water. Okay. This is a good example here. These are mosquitoes, larval mosquitoes. They are air breathers. What they do is they have these siphons, and they push the siphon up through the cohesive tension, and then they spread out hairs. And so when they come back down, the hairs are caught on the surface. It's like they're hanging on coat hangers, hanging off the top there. And so as long as there is surface tension, the larval mosquitoes can breathe. Okay? So soap disrupts surface tension. Okay? So when you put soap into the water, it's going to break surface tension. So can you think of a practical application of soap breaking surface tension when I'm talking about mosquitoes?
The larvae.
Say what?
The larvae will drown because they can't have access to the air.
So the idea is, so there are soap sprays that are used to control mosquitoes. So that's what he's doing. He's spraying this soapy material into these ponds, breaks the surface tension, kills the mosquitoes. Okay. Another characteristic, 46, huh? Peek, see if there's anybody standing out here. Nope, not yet. Keep walking. Okay. Another another important characteristic of water is what's called solvency. Okay. Water, because of that, again, we're back to the whole same problem before, or not problem, same condition before. I got a strong positive end, I got a strong negative end. So anything that's ionic easily bonds with water. Okay, once something bonds with water, it dissolves, basically. So, all cations, anions, hope you remember those names, words mean. Cations tend to bond to the oxygen side, okay, because it's negative. And the anions tend to bond to the hydrogen side, because of that being positive here. So they're showing you this, here is a molecule here with an anion and a cation, probably salt, it's the classic one they show here. So here's the sodium here, here's the chloride here, all the way surrounded by water, broken apart, surrounded by water, it's dissolved. Okay. Water is often referred to as the universal solvent. It is not. What things do not dissolve in water?
Oil.
Oil. What?
Non-polar.
Non-polars. Oil, non-polar. Both of you are correct. Yeah, it doesn't dissolve in water. Okay. But polar, anything polar does dissolve in water. So, what's the value, of course, speaking as biologists and limnologists? This means that water holds nutrients. So let's think of some nutrients. So nutrients, many of the nutrients are cations. Example of cation nutrients. Give me some.
Sodium.
Sodium, okay, give me another one.
Magnesium.
Magnesium. What's magnesium so important for? Do you know? It's extremely important. It's a good one to check. Why is it important for photosynthesis? It is the basis of the chlorophyll molecule. Yeah, it's a chelated chlorophyll molecule. So magnesium, sodium, any others?
Potassium.
Potassium.
Or heart. No, calcium would be.
Calcium. Calcium counts.
Okay, calcium.
Ammonium. Ammonium. Cation. Okay. So all these cations can. Okay. How about some anions that are important?
Chlorine, yeah.
Huh? Chlorine? Yeah.
Yeah.
Yeah. Think of some other ones. Oxygen doesn't play in the game. I'll explain why a little bit later. Okay. Oxygen is not a dissolved nutrient. I hit that really hard. I'm excited that you're okay. Sulfate, nitrate, phosphate. Okay. Those are all some important ones. You know. So like, does anyone know what the number one fertilizer in the world is?
It's just the.
Ammonium nitrate. That's like getting a lot of ends. You take a cation nitrogen and an anion nitrogen, hook them together. Of course, they also blow up. Okay. Okay. And so, uptake for plants to use these, you can't just dump sulfur on a plant. You can't just dump nitrogen on a plant and all that. It has to be dissolved. So water is dependent. So plants are dependent on dissolved substances. So that becomes critically important. The fact that water is substance. And so because it's dissolved, this is how the nutrients move out through surface flow, subsurface flow, groundwater flow. It can change from one place to another. Okay. Sometimes that's good, sometimes that's bad. We'll be talking a lot about how nutrients going into places where they shouldn't be will cause all kinds of problems. Green will be beating that to death. Okay. Temperature affects solvency. Okay. So does solvency go up or down when you warm up water? How so? I want to dissolve a whole bunch of sugar in water. Do I use ice water or hot water?
Hot water.
Hot water. Okay. Right. Solvency goes, okay, warmer the water, there's my T right there. Okay. Warmer water, solvency is high. Colder water, solvency is low. It changes. So it's going to be an important point I'm going to make a little bit later on when I get to the oxygen. Okay. The other thing is not dissolving, but what we often refer to as either viscosity or suspension. I'll find out something kind of class in here. Hey, shut up, man. Hey, shut up, man. You guys got class in here? Yeah. Damn it. Okay. Let's see if you see an empty class somewhere. Yeah, thanks. Go. Yeah, we got a class. Blake's out there. Class. Julia. Okay, so let's stop right there. I'm discussing. I'll remember. Let's go back to the class.